Hi all. Today we'll see the model development of a single phase full bridge converter circuit with a RL load. So first of all we will go to Simulink. Meanwhile we'll open a blank model, and meanwhile we'll go for the circuit. This is the single phase fully controlled bridge circuit with the RL load. Our aim is to model this circuit and obtain the corresponding waveforms across load as well as supply, as well as thyristor, supply current, output load current, etc. All those things we can view on the scope. Okay, so we'll develop the model of this first. Okay, so for that, what are things necessary? First, we'll bring a power GUI block. Okay, then we need a thyristor switch. No, so we'll make use of a thyristor measurement, but we don't require now. And we'll, as in the circuit diagram, we will rotate this so that it look like in the circuit diagram. We'll take 4 copies of this by pressing the Ctrl C button, and okay, 4 models are there now. Okay, and now we need an AC voltage source. No, we'll search for the AC voltage source. Okay, take an AC voltage source. Okay, and if we need a 230 volt AC supply, it will be 230 root to the peak. No, so let it be 325 and let it be 50 hertz AC. Okay, and this anode to cathode and this anode to cathode we have to short, and we'll give supply to this and this into the negative and to the side. Okay, and we need a pulse generator. No, whose output will be given to this, and we know that we need to switch on this as well as this. Means say thyristor, let it be thyristor 1, and this let it be thyristor 3. No, this will be your thyristor 2. Normal nomenclature is like that. No, this 2 and this 4. We'll complete the circuit now. We had brought current measurement, voltage measurement, then a scope, then an RL series element. We'll connect it to through the current measurement device. We'll connect it to the load. Okay, this to the load. Okay. Okay, and we need to connect the pulse generator output to, so let this be the pulse generator 1. It is, as it's a bridge, we need to give same input, same at the same time we need to switch on thyristor 1 and 2. So we'll give the same pulse output to 1 and 2. Similarly, we'll make a pulse generator 2 here, and we'll bring a block like that, and we will give input to that 3 and 4. Thyristors 3 and 4 will be given input from pulse generator 2, so that once this pulse is on, these two will be triggered at a time, and once this pulse is given during the positive half cycle, then T1 and T2 will be on. When during negative half cycle, pulse generator 2 will be on, so T3 and T4 will be on. Okay, and let there be a scope, and its layout, let it be 4 input. We should number of input ports, let it be 4. Okay, and okay, and let's say 4 input we are giving. Okay, and this we need to get the output voltage, so we will measure the output voltage, and let this be our output voltage. We need to get the output. This is your output voltage. Again, we will put a voltage measurement across input voltage. So we had given the input voltage waveform to scope, and the output voltage is also given. Let us measure the input current as well as the output current also. Okay, so if we need to measure this input current, we need a current measuring device here. So let us bring that. Now we had brought a current measuring device there. Let us place. It's okay. Let this be, what is this actually? This is your I source, no, IS, let it be IS, and this we mark it as a VS. Okay, this is your V0 and this is your I0 now. I0, V0. Okay, and then what are things remaining? So, and suppose let us bring one more scope here in order to simply see the pulse generator output 1, pulse generator output 2, and what is the voltage across the thyristor also. Okay, let us do it later on. Okay, first we'll make it to number of inputs, let it be 2 alone. Okay, okay, let us run it for simulation time is already given us 10. Let it run it for 10 seconds. Okay, before that actually we haven't made all these elements, we haven't checked. No, this is your input voltage. Okay, this is your pulse generator. No, it's our pulse generator. Let it be, period is 1/50. No, because we are doing it for 50 Hz AC. Pulse width, let it be 20%. Phase delay, let us make it 0 itself. Okay, so this generator should be during the other negative half cycle only. No, so here again pulse width 20, duty cycle 1/50. And what about phase delay? Phase delay is 1/2 cycle. No, 1/2 cycle actually corresponds to 10 millisecond. No, so let us give it in seconds as 0.010. Okay, and that's it. Then thyristor. And what about load? Let us take the current resistance as 10. Let it be 100. Okay, we have given 10 ohm resistance and 100 millihenry as the inductance. Okay, simply do. Okay, let's run it. You want to observe the waveforms. Okay, it's V0, I0. What is that voltage measurement? This, no, let us mark it as VS alone. Okay, source voltage. Okay, So this is the waveforms. That is what we actually expect. No, this is our supply voltage, 230 volt AC. Okay, and every half cycle it is being converted to positive half cycles as well as negative half cycles converted DC. This is the supply current taken from the supply. No, this. Okay, whereas this is the same goes on like this. No, that is a load current. Okay, we'll see the waveforms of pulse generator also. This is the pulse generator output. Okay, clear? That is correct. What we have expected, we got it. And let us add one more. Okay, that's let us add one more here. Okay, so that it's visible like this. Okay, we want to add two more inputs like the. Okay, just to show the thyristor voltages. So for that we need a voltage measuring device there. We'll bring that. So here we have taken the voltage across this thyristor as VT1 and this thyristor as VT2. Now let us see. Okay, this is the okay. This once this is here is on. This is for pulse generator 1. It is given in means VT1 is on. On means it's 0. When it is off, we are getting the full input voltage across that. Similarly, VT2 also. When pulse generator 2 is given in means its positive half cycle, it is truncated. Only negative is there. Okay. Now we will see if we delay it by some phase delay. Let us give some phase delay as say 0.03. Okay, so once 0.03 second delayed by pulse generator 1 means pulse generator 2 also has to be delayed by 0.03 from the very starting of this. No, this has to be 0.10 millisecond, 3 millisecond delay. Here again 3 millisecond delay what we need, actually not 30 millisecond, actually 3 millisecond. Sorry. Okay. Now see. Okay, and all changes happen. You can see this is this continued for this duration. No, it has truncated there. Okay, waveform changes. No, similar is the case with this pulse generator waveform when it is shifted by 0.003 or 3 millisecond. How the SCR voltage across the thyristor also got changed. Okay. Now we will add a diode to the freewheeling diode. Okay. At the output side. Don't need. Okay. We'll rotate it. This was the output voltage waveform. We have given a alpha corresponding to 0.003 or 3 millisecond time. around, okay, like this. Waveform is like this. Okay, now we will run with the freewheeling diode. Actually, let us run it. See the waveforms. Now look the waveforms. This is the output voltage is getting truncated, the negative cycles being truncated, and this is the current waveform, source current. And let's see. This is the source current, this is the output current. Okay, we are getting as we expected, no? Okay, we will change the pulse delay to say alpha corresponding to 90° means it is 0.5 millisecond, no? So let it be 0.003 seconds, and let this be 0.015. Okay, let us apply it. So we see. Waveforms. Okay, it's 90°. It is the alpha value 90°. From 90 to 180 it is there. Then the second cycle starts only at here, no? So current taken from the mains when these pulses are on, but the load current is there continuously. So this during this much, not only this much duration, it is getting replaced because it's a highly R load, inductive load. Okay, hope it is clear. Thank you.